Yeah, now you're experts on basically planes, directions, families of planes, families of directions. You know when to use this notation, you know when to use this notation, you know when to use this notation, and this notation, et cetera, et cetera, et cetera. So you're all experts on that in this point. Now we want to build up from, again, and actually fully develop our kind of 3D structures. So in this course, we're going to be focusing a lot on the cubic system, specifically simple cubic, body-centered cubic, face-centered cubic, and we'll also get into hexagonal post-packed briefly as well. But these are going to be the focuses in this class. So let's go ahead and start simple with simple cubic. My jokes are getting great, aren't they? So simple cubic cell. Let's go ahead and draw this out. So in the simple cubic cell, we have basically only atoms at the corners. So we have 8 atoms here in 3 dimensions. And when we're kind of describing our kind of primitive lattices and our kind of basis angles, and we kind of use this alpha angle between A2 and A3, beta, gamma, we're going to use kind of this notation. And to describe the cell in 3D, this, for example, is going to be A1. This is going to be A2. Oops, let me change that. Change. Switch to green. This is going to be A2. I see I switched also from A1. Let's do black. And this is going to be A3. So you can kind of see those directions, and you can see kind of the different angles that are going to be the approach here as well. So you can kind of see those interaction angles. They're all 90. Again, that's going to hold for every kind of structure. So they're always going to be kind of 90, and you can see the directions right here. Now, the key point here is when we draw these kind of structures, we're drawing spaces between kind of these atoms here. But in reality, the cell doesn't look like that. In actuality, these kind of atoms are touching. So actually, I'm going to go ahead and bring up our, sorry for kind of bringing this up now, but I like to do this kind of very naturally and on the fly. Let's bring up our, let's see, our lecture notes, lectures. Don't show you your exam coming up. No, just joking. Not yet. Soon, but not yet. So let's go ahead and look at our kind of structure. Look at some figures that might be useful for visualization purposes for simple cubic. So for simple cubic, we're actually seeing kind of a structure like this. So you can see here the atoms are touching. So the atoms here are, touching in this structure. So what we see here, oops, it depends. I want to be able to kind of, edit it. So let's just kind of break it out right here. So here you can see there's an atom that has a radius r here, and an atom that has another radius r here. So this lattice parameter, which we typically call A, again, magnitude here, RA for simple cubic, because those atoms are touching, A is equal to 2r, 2 times the radius of our atoms. This is going to be very important. We're going to move forward. This is going to be very important moving forward in kind of this structure, because this distance, this lattice parameter, is going to change depending on kind of the structure or the type of cubic cell, i.e. simple cubic, BCC, FCC that we're dealing with. But here we can see again the distance here is going to be 2a. So here a is equal to 2r, a is equal to b equals to c equals, a is equal to 2r. And the key thing is here, you're always, for any kind of material, your nearest neighbor distance, NND, is always going to be 2r. This holds for any type of cell that you can deal with, because we can't get closer than 2r. So that is your nearest neighbor distance. So distance here. So the next question asked is, how many atoms are contained in our unit cell? Is this a primitive unit cell? So this question is a little bit kind of difficult to kind of visualize, but we have to kind of think about now in 3D, right? So looking at a single atom, so let's say this atom right here, how many atoms is it shared with, or how many unit cells is it shared with? Well, it's shared with 1 here, but remember, we're in 3D, right? So there's a cell going out here, there's a cell going out here, there's a cell going out in this direction as well, there's going to be a cell on the bottom. So basically, you can kind of imagine it's going to be 4 here and then 4 on the bottom. So each of these corner atoms, so in 3 dimensions for cubic structure, corner atoms, so let's go ahead and move to the next page, unfortunately. Ooh, I might be lost on, on what page we're at, actually. So let's see. Yeah, here we go. So each of these atoms for cubic materials, the corner atoms are going to be an eighth. So an eighth contribution for corner atoms. Corner atoms. So that's going to be our kind of contribution. So I have 8 corner atoms. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So how many atoms in our cell? 1/8 times an eighth, 1. How many number of nearest neighbors does each of these atoms have? Again, this is kind of a difficult thing to kind of visualize in 3D, but you can imagine this would be my nearest neighbor here. There's a nearest neighbor here. There'd be a nearest neighbor coming up here, nearest neighbor here, nearest neighbor here, nearest neighbor here. So 1, 2, 3, 4, 5, 6. Again, hard to see in 3D, but again, look at the Mathematica notebook and you can get some idea. So 6 nearest neighbors, second nearest neighbors, you don't really need to know this too much. Nearest neighbor distance, always a 2r. Second nearest neighbor or next nearest neighbor distance, you can kind of imagine here, right? This would be my next nearest neighbor distance. I'm going to draw this black. And that's across my diagonal. So again, we need to kind of go back to our kind of geometry here. So if I have atoms here, again, for this atom, the next nearest neighbor distance would be right here. So if we're looking at this distance, the blue here, we know that here, this is A. So we know that this distance is going to be √2 of A. And we know that A is equal to 2r. So get ready for some, again, geometry here. What about the atomic packing factor? So the atomic packing factor, or our APF, is a very, very, very important metric for materials. Why? What is this atomic packing factor kind of accounting for? Well, it is equal to the volume occupied by atoms divided by volume of cell total. So what is the maximum packing fraction, or what's the maximum volume that can be occupied by basically spheres in a kind of cube? So if I have a cube, what is the maximum density, or what's the maximum atomic packing factor or fraction of basically spheres of the same size with radius r that I could fit into a cubic cell? Well, hopefully if you remember back to some kind of geometry, the magic number there is 0.74. That's the maximum packing factor that I can get there. Now, why is it important that we kind of know, like, if something, and if we have that, if we meet this condition, if our APF equals 0.74, we call this a close packed structure. Why do we need to know this for materials? Well, because, we'll get into this again in the future, if the atoms are very, very close together, usually kind of when we look at dislocation, motion, and shear and movement of atoms, or diffusion as well, we want to jump to kind of nearest neighbor locations, and it's easier to move or kind of slide these dislocations in close packed planes and close packed structures. So they often are more ductile. So again, structure dictates property. That's why we're kind of focusing on this course. So let's see what's the atomic packing factor of the structure, of our unit cell. So let's go ahead and do that. I might kind of head over here because I want to show this in person. So I've got my simple cubic here. So what's the volume of this sphere that has some radius r? So I know that APF is equal to the number of atoms, which is, in this case, for simple cubic, 1 times the volume of that atom, which is 4/3 pi r cubed. What's the volume of my cube, of my unit cell, my simple cubic unit cell? Well, it's A cubed, where A is equal to 2r. So this is going to be 2 times 2 times 2 is going to be 8 pi r, or actually, excuse me, not 8 pi, 8 r cubed. So when we go ahead and kind of work with this, so let's get these cancel out here. So it's 4/24, which is going to be 1/6. So our APF is equal to pi over 6. And if you look at pi over 6, if we evaluate that in Mathematica real quickly here, let's see that pi divided by 6, numerically, that is not 0.74. It's 0.523. So that is not a close packed structure. So our simple cubic is not close packed. So as we can kind of see here. Not a close packed structure. Let's move on to our second structure in the next video, body-centered cubic, and see if that happens to be a close packed structure. So I'll see you all then.